Hello and welcome to another read-along for college geometry, a problem-solving approach. Today we are going to read through section 1.2, more problem-solving strategies. Specifically, this will give us 3 new strategies we can use and some of the most powerful tools. In this section, we will continue to examine strategies useful in solving problems in geometry. You will often use the 3 strategies presented in this section together in solving a given problem. In fact, at times it may be difficult to solve a problem using only one of these strategies and not employing any others. The same is true for many of the strategies we will discuss in this book. It is probably more common to use a combination of strategies in solving a problem than it is to use one particular strategy. That's so good, I'm going to highlight that. This is a good thing to keep in mind, especially as you are working through some of the exercises, and to not be dismayed that a single strategy didn't get you as far as you wanted. For example, frequently the first step in solving a problem is to play with the problem using the guess and test strategy or the draw a picture strategy. After we spend some time on a problem in this way, we may decide to use a variable to write an equation or begin to look for a pattern. And this is kind of brought up indirectly in the list of clues that it gave us that these strategies would be useful for both guess and test and draw a picture. It mentioned you wanted to gain a better understanding. That was step 1 of our problem-solving cycle. And to get a better understanding, you could just start testing and drawing pictures before implementing your true strategy that will lead to the solution. So here, then, is our first tried and true strategy for the solution of this section. Number 4, look for a pattern. Much of mathematics consists of observing and describing patterns. We can observe patterns in sequences of numbers, relationships between numbers, and in geometric figures. In fact, one could almost describe mathematics itself as a study of patterns. We often use the look for a pattern method in conjunction with other problem-solving strategies, such as make a table or solve a simpler problem, which we will discuss soon. The following clues may help you to identify situations where the look for a pattern strategy may be useful. And since we already talked about combining strategies, I'm going to make a note here about these combined strategies, just kind of to remind ourselves of some possible synergy, right? Those fancy industry buzzwords. So some clues where you might want to look for a pattern. The problem gives a list of data. The problem involves a sequence of numbers or figures. List, sequence. Listing special cases helps you to deal with a complex problem. Special cases. The problem asks you to make a prediction or a generalization. That almost necessitates finding the pattern to then determine what comes next. You can express or view information in an organized manner, such as in a table. Okay, any organization could be roots of a pattern. So here is an excellent example of this strategy at work. Problem, we can arrange toothpicks to form rows of squares as shown in figure 1.10. How many toothpicks are required to form a row of 100 squares in this manner? Okay, so let's take a look at figure 1.10. Row of just 1 square, 2 squares. Notice it is not 2 separate squares, but they are conjoined and share this toothpick in the middle. And then 3 squares, and so on. And then this one refers to some other problem, so just these straight rows of squares. Okay, let's see. Just to get some conceptual understanding here. Notice we cannot break the toothpicks. That's not allowed. We must arrange the toothpicks in a straight line of squares, not a stacked array like this thing. For example, the arrangement in 111 would not be acceptable. We must determine the number of toothpicks to form a row of 100 squares. Well, I mean, you could keep extending this out and draw it all the way out and then count that up. That's possible, but it seems like that would take an awfully long time. What's a better idea? Well, we might try a few more rows of squares, say 4 squares and 5 squares. Then we could examine the results to see if there appears to be a relationship between the number of squares and the number of toothpicks, right? A relationship between number of squares and number of toothpicks. So we're trying to find that pattern. Notice we've already determined that 3 was not enough. We want to go to 4 or 5 just to be sure we have the proper pattern there. So we do that. Create a row of 4 and a row of 5 using 13 and 16 toothpicks respectively. So to summarize, so far 1 square took 4, but to get 2 squares that only needed 7. The 3 squares took 10, then we went to 13, and then 16. So it appears that for each additional square, 3 more toothpicks are required. Therefore, we can say the row with 100 squares will require 3 more toothpicks than the row with 99. Great, so we save ourselves 1 step. But how many toothpicks are required for the row with 99? We would prefer not to count out so many toothpicks. Looking at the pictured rows of squares, we might also observe a visual pattern. A row of 2 squares consists of 2 sets of 3 toothpicks plus a single toothpick necessary to complete the last square. Oh, there's another way. So look at this. They're breaking down the squares into this C shape plus a C shape plus the final toothpick. Similarly, a row of 3 squares consists of 3 sets of 3 toothpicks plus a single toothpick, and a row of 4 squares consists of 4 sets of 3 toothpicks plus a single. So again, we have C, 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 forming 1, 2, 3, 4 almost squares, plus that extra to get that 4th square solidified. Ah, clever. So a row of 5 squares would require 5 sets of 3 toothpicks plus 1 single toothpick, or a total of 5 times 3 plus 1 equaling 16. That's exactly what we found earlier. This means that a row of 100 squares would require 100 sets of 3 toothpicks plus 1 more toothpick to complete the last square. So the total number of toothpicks necessary for a row of 100 squares would be 100 times 3 plus 1, 301. You may observe other visual patterns for this problem, but they should all lead to the same final answer, namely 301 toothpicks. Right? This is just acknowledging that there are other ways to break this down, but you'll still get that same formula. In fact, speaking of formulas, let's go 1 step further. Step 4, looking back. How many toothpicks would be required for other rows of squares? We could use a variable to generalize the pattern we have observed. If we let n be the number of squares in a row, then we can calculate the number of toothpicks required as in step 3. The row would require n sets of 3 toothpicks plus 1 more toothpick. So the total number of toothpicks required would be n times 3 plus 1, or 3n plus 1. We can also use this formula to determine the number of toothpicks required to form a row of any size. Hey, that's handy. Lots of problems come up and ask about what about any size. For example, a row of 200 squares would require 3 times 200 plus 1, or 601 toothpicks. There you go. All right, so more generally speaking now, in the preceding toothpick problem, we observed 5 different examples of rows of toothpicks, noticed a pattern, and then concluded that this pattern would hold for any row of any length. When we look at specific examples and draw a general conclusion from the pattern observed, we are using what is called inductive reasoning. Look at specific examples to draw a general conclusion, right? following a pattern or going from specific to general is inductive reasoning. We often use inductive reasoning to draw conclusions. For example, scientists reason inductively when they perform experiments, observe the results, and form a hypothesis to explain those results. Right? That's often what the laws of physics and nature are a result of. You only experimented on a certain region, but you now drew a general rule for how the rest of the universe behaves. Mathematically now, we may observe the sequence of numbers 5, 7, 11, 13, 17, 19, 23. Notice a pattern. The differences between successive terms alternate between 2 and 4. That is, 7 minus 5 is 2, 11 minus 7 is 4, 13 minus 11 is 2, so on. Or you could go back and think, how much do I add? Right? From 5 to 7 plus 2, then from 7 to 11 plus 4, and then plus 2, plus 4, plus 2, plus 4. Reasoning inductively, we may predict that the next number in this sequence, I added 4 here, so should be 2 more than 23, 25. That sounds perfectly logical. In the situations involving inductive reasoning described so far, we observed specific examples and drew a general conclusion, right? Specific to general. This transition from the specific to the general is the essence of inductive reasoning and distinguishes it from deductive reasoning, which is used extensively in geometry. In deductive reasoning, some general statements are accepted as true, and then specific conclusions are drawn from those statements. Highlight that bolded vocabulary term. Deductive reasoning goes from general down to the specific. We will use both inductive and deductive reasoning in geometry. Deductive reasoning will be a major focus of our study in Chapter 4, so something to remember for later. But something that will definitely be applied even before then. We must consider one pitfall of inductive reasoning. Based on our observations of a few examples, we conclude that the pattern we notice will continue and that it is the only correct one. This assumption may not be warranted. For example, in the case of the numerical sequence, 5, 7, 11, 13, 17, 19, 23, we just took a look at that, it may seem reasonable to assume that the next term will be 25. However, it is just as reasonable to predict that the next term will be 29 because all numbers listed are prime numbers. Just as reasonable. Positive integers that only have 2 factors, right? Reminding us of what prime numbers are. And the next prime number after 23 would be 29. Thus, in this example, more than one valid conclusion is possible. Due to this difficulty, we often use a combination of inductive and deductive reasoning to justify a conclusion. Combination of inductive and deductive to justify a conclusion. Inductive is great for finding new patterns. Okay? Let me write that down. Inductive is great for finding patterns. Okay? But deductive is necessary for proving it. Right? If you want to be sure that that's the case, then you need to employ deductive reasoning. Yes, this must be the one because it takes the general rule that is already established as true and applies it to the new scenario. So, if you want to test your pattern finding skills, try the following additional problems. Number 1, examine the sequence of rectangles with subdivisions and shading as shown in figure 115. Draw the figure that would come next in the sequence. And I realize this copy does not make the shading very immediately obvious. So first we have this rectangle with half that shaded in, then we have this rectangle with that quarter shaded in, and then that segment shaded in, and then this little segment is the only one shaded here. As a few hints to get started, compare consecutive figures and consider the size and position of the shaded region in each of them. What do you observe about the orientation of the large rectangle? That also changes, right? Try focusing on only one attribute at a time and follow it through the sequence to figures from left to right. Right? This is very useful when dealing with these pictorial patterns because there is almost always more than one thing going on. It is definitely recommended to just find one change at a time. All right, and then the second problem is thus: the rectangular numbers are the positive integers that represent the total number of dots in the arrays shown in figure 116. Here we have two dots. And then the second one we have 6 dots. And then 7, 8, 9, 10, 11, 12 dots, and so on. Notice they form a nice, neat rectangle. Right? Notice that there are 6 dots in the second array, so the second rectangular number is 6. There are 12 dots in the third array, so the third rectangular number is 12. Find the number of dots in the nth rectangular number. There's that nth. They're looking for the general rule here. Okay, go ahead and pause here now to give these two problems some consideration, and we will visit the answers at the end of the video. All right, now that you've tested your mettle on those problems, let's look at strategy number 5, make a table. It is often helpful to make a list or a table when searching for a pattern. For instance, in example 1.4, we calculated and recorded the number of toothpicks for rows of different sizes. We could have neatly summarized these data in a table such as table 1.1, shown next. Here we are, right? And they almost virtually did write out a table, just with many more words to write each line as we go. So here we only have to title each column once. If you're whipping this up, drawing it by hand, no, it doesn't need to be as neat. I often don't put the extra border around the outside of my tables. But it does provide much nicer organization and easy to read data at a glance. Arranging data in a table such as table 1.1 may make patterns easier to recognize. For example, we might observe that adding 2 to each number in the right column yields a column of numbers that are multiples of 3. You will often see tables combined with the look for a pattern strategy. Right? Adding 2 to each number in the right column. Really? Plus 2 is 6. Plus 2 is 9. Plus 2 is 12. Oh, look at that. Look at that. We've created a third column now. Call it the plus 2 column. Get there. Looky there. Okay. A table can also provide a convenient means for systematically recording guesses when applying the guess and test strategy. A table is a good way to organize data as they are generated, summarize information given in a problem, or list possible values of variables. The following clues may help you to identify situations where make a table strategy might be useful. So we have you can easily organize and present information. If you will generate data anytime, so think If this could be a science experiment or thought of as a science experiment, I will set something up, try something, test, get result. Change systematically each time to test and get new results, right? That's the data generation. You want to list the results obtained by using guess and test. The problem asks in how many ways something can be done. Again, you need to be able to keep track of all of those ways that you've found, so make a table. You are trying to learn about a collection of numbers or figures generated by a rule or formula. Okay, so if you're already given a rule or formula, one way to visualize how that formula evolves is to create a table. The next step from that would be then to possibly generate a graph like you might do in algebra class. All right, here's a great example for table making. A man wishes to enclose a rectangular area of 100 square feet for his dog. Right? He's going to fence in a piece of yard for the dog to run. He is considering rectangles with whole number dimensions. What dimensions would require the least amount of fencing? Okay, whole numbers and least amount of fencing. So we're trying to minimize something here. You might recognize a similar type of problem from calculus, minimization problems. That whole number will make our job much simpler and also a lot more practical. I know if I was putting in a fence, I would not be trying to make it 15 2/3 of a foot long. It's very difficult to purchase supplies that way. Right, so the rectangle must have an area of exactly 100 square feet, and its dimensions must be whole numbers. In order for the amount of fencing to be as small as possible, the perimeter of the rectangle must be as small as possible. Okay, so we're interpreting, right, least amount of fencing. What is mathematically, how do you get that? Perimeter. Recall that the area of a rectangle is A equals L times W, and that the perimeter of a rectangle is P equals 2L plus 2W, or P equals 2 times quantity L plus W. We must determine the length and width that give the smallest perimeter. Well, why don't we test them? Right? What lengths and widths give an area of 100 square feet? What are the possible results? Make a table summarizing the possible dimensions and showing the perimeter in each case. Right? You might quickly decide that this would take too long. Right? But this is a great, at least, first start. Like, why don't we guess and test a few from it? But we want to organize our guesses, so we're creating a table. And if at some point you realize, oh wait, there's actually like 50 possible combinations, maybe it's too much, maybe then you'll look for a different plan. Right? But let's start with this. Carry out the plan. Possible lengths and widths are summarized here. It could be 1 by 100, 2 by 50, 4 by 25, 5 by 20, or 10 by 10. And of course, we can go reverse and back to 20 by 5, but then that would be the same thing as this. Every time the area given is still 100, but notice the perimeters. For a long, skinny rectangle, a 1 by 100, you get a perimeter of 202. And then it slowly decreases until the smallest value here found is 40. Because 1, 2, 4, 5, 10, 20, 25, 50, and 100 are the only whole number factors of 100, the table shown contains all possible dimensions for the rectangle. Okay? You have to be able to justify that I definitely found all the possibilities. Therefore, the minimum perimeter is 40 feet. And it occurs when the rectangle measures 10 feet by 10 feet. Notice that the rectangle with the minimum perimeter, in this case, is a square. A square is a special type of rectangle. And in fact, you will find this to almost always be the case. The perimeter with the minimum, rectangle with minimum perimeter is a square. This is one of the reasons that soap bubbles are round. Is even better than a square actually would be to create a circle, and in 3 dimensions a sphere. Gives you the most area for the perimeter, or the most volume per surface area. Looking back, will a square always give the minimum perimeter? Try rectangles with different areas. It does, it's true, I'm telling you. Would it make a difference if only 3 sides of the enclosure were fenced and the 4th side was against a garage? Oh, okay, only 3 sides. Well, then you got me there. Then it's not automatically a square because one of the sides is not included in the fencing total. Okay? At that point, it does start to differentiate. Good thing to consider there. All right, if you want to test your mettle with the making a table strategy, here are a couple sample problems you can try. A square piece of plywood measures 5 inches by 5 inches. That's a tiny little scrap there. In how many ways can it be cut into smaller pieces such that each of the smaller pieces is a square with whole number dimensions? Note, 2 solutions are considered to be the same if they result in the same number and size of pieces. All right, so to give you an idea, here's a few pictures here. We've got a full 5 by 5. You could cut it all up into single 1 by 1s, or you could go 1 by 1s around the edge and one large 4 by 4. If instead you had the 4 by 4 over here and then 1s along these edges, that would count as the same result. And we are not considering any kerf caused by any saw blade in cutting the actual plywood. So some tips before you begin. Here you might want to use both a draw picture and make a table strategy. You could make a table of pictures. There are, in fact, many solutions. One possibility is that the square can be cut into 25 squares, 1 inch on a side. Squares that result need not have the same dimensions. For example, some of the piece might be 1 by 1 squares, and one piece might be a 4 by 4 square. We have here. What dimensions are possible for these smaller squares? You might list those possibilities as headings in a table. What possible sizes are there even to consider? And the second problem, a dartboard consisting of 4 circles as shown in figure 119. Here we go. 1, 2, 3, 4. 3 colors, red, yellow, and black, are available to repaint the board. If the bullseye of the dartboard is to be red, and no 2 bordering circles can be the same color, how many different color schemes are possible? Okay. There you go. Go ahead and pause the video here, give those problems a try, and come back and we'll have the answers at the end of the video. All right, now that you've had a brain break, let's continue on to learn about our final strategy of the chapter, number 6, possibly the most powerful of them all, solve a simpler problem. If the numbers in a problem are very large, very small, like we're talking tiny fractions and decimals here, or difficult to work with, it is often helpful to solve a simpler version of the same problem. For example, large numbers you may replace with smaller, more manageable numbers, or numbers involving many decimal places you may replace with whole numbers. Once a technique is found for solving the simpler problem, you can often use the same technique to solve the original problem. For instance, in example 1.4, we wanted to determine the number of toothpicks necessary to form 100 squares. Rather than solve the problem with 100 squares right away, we studied several simpler problems. We examined the rows consisting of 3, 4, and 5 squares, and we observed a pattern that could be extended to the case of 100 squares. We can also use the solve a simpler problem strategy when a figure is complex. We can look at a simpler version of the same figure and see if a pattern emerges that will lead us to a solution of the original problem. The following clues may help you identify situations the solve a simpler problem strategy might be useful. Notice something that is brought up a lot in here. It's not just find a simpler version, okay? You're going to find a simpler version, use those same techniques. So you're going to treat the simpler problem as practice. For the same reason that we are practicing with these problems here to gain experience in seeing types of problems that you can then recognize in the future, you're creating your own miniature practice problem inside the problem. First, get experience working there, and then now say, oh, I know how to solve that type of problem. And the original problem is now that type of problem. We should also point out that when we worked with this simpler version, what we did is we observed a pattern. Took a simpler version, the same figure, see if a pattern emerges, okay, to identify those situations. So solving a simpler problem is also an extension of finding a pattern. You're just starting on the small end to make it easier to find the pattern, and you want to make sure the pattern can be extended out to the full version. Let's take a look at those clues now. Solving a simpler problem might be appropriate when the problem involves complicated computations. Okay? The problem involves very large or very small numbers. A direct solution is too complex. You want to gain a better understanding of the problem, similar to just drawing a picture. Try to test the basic version first. The problem involves a large array or diagram. So here is a classic problem, the handshake problem. Okay, I think every mathematician has had to solve this problem at one point or another in their career. There are 20 people at a party. If each person shakes hands with every other person at the party, how many handshakes will there be? Total number of handshakes that happen. Okay? Some other observer is counting them up. Each person, let's understand the problem first. Step one. Each person must shake hands with every other person exactly once. If person A shakes hands with person B, then person B does not shake hands with person A again. We must count the number of handshakes that occur and avoid duplication. This is often the kryptonite of many problems. It seems simple at first, then you realize, oh wait, what about the double counts? Rats. And it makes the computation that much more complicated. So let's see what we can do here. We might represent the people as points on a circle and draw a line segment to represent each handshake. For example, the line segment joining A and B represents person A and B shaking hands. Figure 120. Over here, oh my gosh, that's a lot. Look at all those lines. Person A shakes hands with this guy, this guy, this guy. Right? All of these people around here. Here's person B on the other side of the room. All right. Well, that figure shows all the handshakes for A. If you draw the line segments for the remaining handshakes, it'll be very difficult to count all of them. Oh gosh, yes. So let's just imagine, right, we've got to now connect this person shakes hands there and there and there. It's going to get very messy. Very difficult to count all of them. However, we can more easily solve simpler problems involving parties with fewer people. Okay? It didn't say we have to start at 20. Figure 121 shows the results for parties with 2, 3, and 4 people. So let's start with a much smaller number, much easier to work with. We can draw our picture. We can guess and test with these small values. We can find the pattern involved and then extrapolate that back to the larger problem at hand. Aha, handshakes. So here we go. 2 people, A to B, 1 handshake. 3 people, A, B, and C. Notice we still have that handshake there, and now C joins in, adds 2 more. So 2 for A, and then 1 extra for person B. 4 people now. A shakes 3 hands 2 additional ones for person B, and then 1 extra for between C and D. And if that's not clear enough, we can put it all together in a table. Oh my gosh, this problem has everything. Number of people, 2, 3, 4, 5. Of course, we didn't actually draw out 5, so we're extrapolating here. But look at the pattern. 1, and then 1 plus 2, 1 plus 2 plus 3, 1, 2, 3, 4 would be next, total of 10. So, based on the pattern in the table, we might calculate that the number of handshakes for 6 people would be 5 plus 4 plus 3 plus 2 plus 1, 15. Therefore, for any number of people, say n, the number of handshakes would be n minus 1 plus n minus 2 plus all the way down to 2 plus 1. So, for 20 people, the number of handshakes would be 19 plus 18 plus 17 plus all the middle stuff, 3, 2, 1. Geez, that's still kind of a lot to do by hand. Even on a calculator, that's a lot of button presses. We can use another pattern to find this sum. Notice that if we pair terms as shown next, the sum of each pair of terms is 20, with 10 being an unpaired number in the middle. Oh, look at that, clever. Put the first and the last. 19 plus 1 is 20. 18 plus 2 is 20. 17 plus 3 is 20. So on and so forth, except 10 in the middle. So all those 20s together, plus the extra 10, there would be a total of 9 pairs of terms, right? Everything after 10, 1 through 9. In case it wasn't obvious, you don't have to count them by hand. They're all counted right here for you. 1 through up to, but not including 10, so 9. 9 pairs of terms, where each pair adds up to 20, plus the leftover middle term of 10. So we could say that the total number of handshakes would be 9 times 20 plus 10 equals 180 plus 10, or 190. Very nice, very nice. All right, step 4, let's reflect a bit. Consider, is there another way we could solve this problem? There's multiple approaches, different ways to represent it, different ways to get started. Also, if n represents the number of people at the party, can we find a general formula for the number of handshakes? Okay. I find it rather interesting that we started with 20 people and our pairing sums always came to 20. Is that going to be always the case? So is it always n times 9? Well, would the 9 change? Would the 10 change? How does that affect our computational result? Something to consider. If you want to stretch your legs even further, here are some additional problems where solving a simpler version will be useful. The first, how many squares of all sizes are there on an 8 by 8 checkerboard? Some of the exercises from section 1.1 asked about how many squares of all sizes, but they never went to 8 by 8. Goodness. You should probably start by drawing a smaller 2 by 2 or a 3 by 3 checkerboard, counting the number of squares of all sizes formed. Several checkerboards of each size may be easier to use than a single checkerboard, right? Draw multiple drawings here. Listing the number of squares of various sizes in a table might help you to better keep track of the number of squares. For example, in the case of the 3 by 3 checkerboard, you would want to list the number of different 1 by 1s, the 2 by 2s, and the 3 by 3 squares on the board. Can you see a pattern in the number of squares of each size for each checkerboard? Right, so how many 1 by 1s? How does that go up? How does the number of 2 by 2s increase? How does the number of 3 by 3s increase as you increase the size of the board? The sooner you can find each of those patterns, you can get your total then for the full 8 by 8 and just add up all the possible sizes. And then our second problem, a schoolroom has 13 different desks and 13 different chairs. Suppose you want to arrange the desks and chairs so that each desk has a chair with it. That sounds reasonable for a classroom. How many such arrangements are possible? Assume that desk number 1 paired with chair number 1 is a different arrangement from desk number 1 paired with chair number 2. All right? So they said unique desks and chairs. How many different arrangements can you pair them up with? Permutation combination going on. Go ahead and pause the video there. Give those two problems a try. Okay, welcome back. Here we go. Spoilers for the additional problem. For the looking for a pattern, here is our drawn in result and our formula n times n plus 1. For additional making a table, there are 10 possibilities for the first problem, shown in the table there. And for the dartboard coloring, there are 8 possibilities listed here. And for solving a simpler problem, we have, here is our sum of possible sizes. We get a total of 204 on the checkerboard. And combining all the desks and chairs will yield a grand total of, oh gosh, 6,227,020,800. Okay, and to finish us off, let's look at a little bit of geometry all around us. As the shell of a chambered nautilus grows, it creates a new wall behind its body every few months, as the body itself is growing and growing, forming a spiral array of chambers, shown here. We can approximate a nautilus spiral formed in this way using a sequence of squares whose side lengths follow what is known as the Fibonacci sequence. 1, then 1, and then 2, 3, 5, 8, 13. Let me zoom in on the diagram there so you can see the sizes in action as each square matches the combination of the previous rectangle formed by combining each square. Right? I add on another square and I get a new rectangle. Add another square and I get a new rectangle. So we add a square of that size and keep going, keep going. Fibonacci sequence is a wonderful set of numbers. It shows up almost everywhere, especially throughout nature. Highly recommend studying that in more detail. But that brings us to the problem set for this section, which means we are done with the read along. So thank you for joining me. If you enjoyed the video, do the usual YouTube thing. But for now, so long, farewell, enjoy the rest of your day.